On February 18th, 2021, at 3:55 in the afternoon Eastern Time, a spacecraft the size of a small car fell through the Martian atmosphere at 12,000 miles per hour, and 7 minutes later came to rest on the floor of a crater that had been waiting for something to happen to it for almost 4 billion years. The crater is called Jezero. In Bosnian, the word means lake. It hadn't been a lake since the Noachian period, since before complex life existed on Earth, before the continents took their current shapes, before almost everything that has ever happened in the history of life on this planet had begun. The rover powered on and its cameras opened. What they showed was a flat, rust-colored plain stretching in all directions. A low rim of layered rock to the north, each band a slightly different shade of ochre and brown and rust, each one millions of years of geological time stacked quietly on the one before it. A pale butterscotch sky, fine dust on the ground, shaped into shallow ripples by a wind that had been moving it, unhurried, for longer than anything alive has existed. The rover sat still for a moment. Everything else had been still for a very long time. A year and a half later, a researcher at NASA's Jet Propulsion Laboratory was reviewing spectral data from a rock sample drilled from a site called Wildcat Ridge. She looked at the readout for a long time. Then she looked at it again. Tonight, we follow this story the way it actually unfolded, not as a headline, not as a verdict, but as a slow accumulation of evidence gathered by real instruments, real scientists, and decades of careful work. We'll move from the first landers to the latest drilled samples. We'll spend time with the specific people who've given their careers to this question, what they found, what they published, and what they were careful not to say. We look honestly at the data that supports the possibility of ancient Martian life, and equally honestly at the arguments against it. At the end, we'll sit with what we genuinely don't know. There is no clean answer waiting at the finish. There is something better than that. The actual science, followed all the way to its edge. The question did not begin with NASA. It began in the modern scientific sense on the night of August 22nd, 1877, in an observatory in Milan. Giovanni Schiaparelli was mapping the Martian surface through a 22-centimeter refractor telescope during a particularly close approach of the planet to Earth. He was meticulous, skilled, and working at the edge of what his instrument could resolve. What he recorded across the surface were long, thin, linear features connecting darker regions. He called them canali, channels in Italian, a natural geological term. The English-speaking world translated it as canals. That single mistranslation ignited something. Percival Lowell, a wealthy Boston astronomer with enough money to build his own observatory outside Flagstaff, Arizona, spent nearly 2 decades mapping what he was certain was an ancient Martian civilization's irrigation network, a dying world moving its last water from polar ice caps to equatorial farmland. He published 3 books, he lectured, he drew intricate, confident maps of a world nobody had visited. He was wrong about all of it. Better instruments, cleaner optics, and eventually spacecraft settled the question of Lowell's canals within his own lifetime. But the longing he gave shape to, the specific, almost unbearable human hope that we are not the only ones, that didn't go anywhere. NASA inherited it, along with the obligation to test it properly. The first real test came on July 20th, 1976. Viking 1 touched down on a broad, rocky plain called Chrysi Planitia, the Plains of Gold, at 11:53 in the morning, local Martian time. It was the first spacecraft to successfully land on Mars and stay functional. The images it returned in the first hours showed a rock-strewn, rust-colored desert stretching to a pale pink horizon. Beautiful in a spare way, and apparently empty. But Viking hadn't been sent to take photographs. Tucked inside the lander was a biology laboratory, small enough to fit in a suitcase, sophisticated enough to have taken years to design, containing 3 separate experiments, each conceived by a different scientific team, each designed to catch life by a different method. The reasoning was sound. Nobody knew what Martian life might look like, so they covered as many angles as they could. The most sensitive of the 3 was called the Labeled Release Experiment. It was designed by a NASA scientist named Gilbert Levin, and its logic was almost elegant in its simplicity. Take a small sample of Martian soil. Add a few drops of nutrient broth, water, simple organic compounds, the kind of food a microbe might eat. Tag the carbon in that broth with radioactive carbon-14. If anything in the soil consumes the nutrients and metabolizes them, it will exhale carbon dioxide. And that carbon dioxide, carrying the radioactive tag, will be detectable. On Earth, the result would be unambiguous. Any living soil would respond immediately. The Martian soil responded immediately. Within minutes of the nutrient injection, the labeled release detector registered a sharp release of tagged carbon dioxide, far more than could be explained by simple chemical dissolution. The numbers were, by the metric the experiment was designed to use, positive, the signature of consumption, the signature on Earth of life. The team was not in a position to celebrate, because the gas release, strong at first, tapered off and then stopped. And when a second injection of nutrients was added, the soil didn't respond again. Living organisms, in principle, should keep metabolizing. Whatever had reacted the first time appeared to be exhausted. More like a one-time chemical reaction than an ongoing biological process. The official interpretation, eventually settled on by NASA after months of analysis, the Martian soil contained highly reactive oxidizing compounds, likely hydrogen peroxide or superoxide radicals, that had reacted chemically with the nutrient broth without any biology involved. The same compounds explained a separate finding. The soil appeared to break down organic molecules rather than preserve them. Gilbert Levin never accepted that conclusion. He spent the following decades, right up until his death in 2021, at age 97, publishing papers arguing that his experiment had detected life, that the chemical alternative didn't fully account for every aspect of the data, and that the scientific community had made a premature call in 1976 that it had never seriously revisited. He may have been wrong. The oxidant hypothesis has strong supporting evidence, and most astrobiologists today accept it as the most likely explanation for the Viking results. But most is not all. What the Viking missions left behind wasn't an answer. It was a methodology problem, a recognition that detecting life remotely, in soil we couldn't fully characterize, with instruments that couldn't distinguish between biology and exotic chemistry, was harder than anyone had adequately planned for. The scientists who came after Viking didn't abandon the question. They built better tools. Before we go further into what the missions found, it's worth spending some time with the word scientists use when they're being careful. Biosignature. You'll hear it throughout this story. It appears in peer-reviewed papers, in NASA press releases, in the careful language of researchers who have learned from Viking, from ALH 84001, from decades of close calls, exactly how much weight a single word can carry. Understanding what it actually means, technically, will change how you hear everything that follows. A biosignature is not proof of life. It is not even evidence of life in the strict sense. It is a pattern, chemical, physical, or structural, that living organisms produce more reliably and more abundantly than any non-biological process we know of. The distinction matters enormously because Mars is a chemically active world, and chemistry can produce surprising things without any help from biology. There are three broad categories. Morphological biosignatures are physical shapes, cell walls, microbial mats, the distinctive layered structures called stromatolites, built by microbial communities over thousands of years that you can find in ancient rocks on Earth and in a few living shallow water environments today. These are the most visually compelling biosignatures and the hardest to fake convincingly. They're also the hardest to preserve over billions of years, and the hardest to detect remotely from a rover on the surface of another planet. Chemical biosignatures are specific molecules, amino acids in the ratios that biology produces them, lipid compounds that form the membranes of cells, particular carbon isotope ratios. Life preferentially uses lighter carbon-12 over heavier carbon-13 in a way that leaves a measurable signature in organic material even after the organism is long dead. Methane produced at rates and with seasonal patterns that geological processes struggle to account for. These are what the modern Mars missions have been designed to detect. Contextual biosignatures are subtler and in some ways the most interesting. They're about the combination of findings, the mineral assemblage, the chemical environment, the geological setting, that together create a picture that biology explains more parsimoniously than anything else. No single ingredient proves a meal was cooked, but the right ingredients in the right proportions in the right kind of kitchen starts to suggest something. Think of it this way. You're walking in a forest and you find ash on the ground. That's interesting. Ash could mean lightning, could mean a wildfire. Now you notice the ash is arranged in a rough circle. More interesting. Then you see scorched rocks forming a ring around it, charred wood stacked at one end, the fragmentary remains of food nearby. Each one of those observations has a natural explanation that requires no human involvement. But the combination, the specific arrangement of those specific things in that specific relationship to each other, starts to push the probability in one direction. That's the logic of a biosignature case. Not a single smoking gun, a pattern that life produces and that non-life has a much harder time replicating in full. This is also why false positives matter. Mars is not a passive inert rock. It has active surface chemistry, those oxidants Viking detected, UV-driven reactions in the thin atmosphere, hydrothermal systems that can produce organic compounds entirely without biology. Any claim of a biosignature on Mars has to pass through a gauntlet of alternative explanations, each one rigorously tested before it earns even cautious consideration. The scientists who are most excited about the current Perseverance data understand this better than anyone. They have spent their careers thinking about false positives. They design their instruments specifically to distinguish biology from abiotic chemistry where possible, and to flag ambiguity honestly where it isn't. That they remain excited is not nothing. The rocks Perseverance has been drilling in Jezero crater formed somewhere between 3.5 and 3.9 billion years ago. That number is worth sitting with for a moment, because it is easy to read and very difficult to feel. The Earth itself is 4.5 billion years old. The rocks we're talking about, the ones carrying molecules that have no clean abiotic explanation, formed during Mars's Noachian period, named after the ancient highlands of Noachius Terra, when liquid water was still abundant on the surface. That era predates the first complex life on Earth. It predates the first multicellular organisms by more than 2 billion years. Whatever lived in the Jezero Lake, if anything did, was microbial. Simple, single-celled, chemically basic. The earliest possible version of life. Here is one way to feel the scale. There is a star approximately 4,000 light-years from Earth, well within our own galaxy, unremarkable in every way, whose light you could see tonight if you knew where to look. That light left its source roughly the same time those Martian lake sediments were settling to the bottom of a shallow, mineral-rich body of water on a warmer, wetter Mars. It has been traveling through the void ever since, at the speed of light, without stopping. It is only now arriving. The rocks have been waiting the whole time. The gas here is amber, not the amber of autumn leaves or old glass. Something deeper than that. Something that has no exact equivalent in the colors of Earth. It glows from within, lit by stars so young they have not yet settled into the long, stable burning that will define most of their lives. They are still finding themselves, these stars, still contracting, still brightening, still warming the cloud they were born inside. The light they cast is soft and sourceless. It seems to come from everywhere at once. Dust lanes cut through the color in long, slow curves, dark paths where the gas is dense enough to block the light behind it, carving shapes that have no name because no one has ever been here to name them. Shapes like the shadows of wings, like the space between things. The temperature of the gas is measured in tens of degrees above absolute zero. It is cold beyond any cold a body has ever felt. And yet, it does not feel cold here, exactly. The light is too warm for that. The amber is too present. Deeper in, where the dust thickens and the illumination fades to something barely above darkness, a protostar glows faintly. A knot of matter that has been drawing inward for 100,000 years and is only now, in this long, slow process, beginning to produce more heat than it absorbs. It does not yet know what it is. It only knows inward. Gravity is patient that way. At the edge of the nebula, where the ionized gas meets the cold molecular cloud behind it, the color shifts. Amber gives way to a faint violet, then to nothing. The boundary is not a wall. It is a gradient, a long, slow breath between one kind of place and another. And there is no single point at which you could say, here the nebula ends. Everything here is in motion. Everything here is still. The light continues outward in all directions, carrying the warmth of young stars into a dark that receives it without acknowledgement, without response, as the dark has always done. Viking didn't end the conversation. It redirected it. The 2 decades that followed the 1976 landers were not idle ones. Mars Global Surveyor launched in 1996, mapping the surface with a precision that no Earth-based telescope could match. Mars Pathfinder landed in 1997, carrying a small rover named Sojourner that trundled across a floodplain and nudged rocks and proved, in a modest but important way, that mobile exploration was possible. Each mission added a layer to the picture. Each layer made the next question sharper. Then, in January 2004, two rovers arrived within 3 weeks of each other. Spirit touched down in Gusev crater. Opportunity landed on the opposite side of the planet, at a place called Meridiani Planum, chosen partly because orbital data suggested it contained a mineral called gray hematite, a mineral that, on Earth, typically forms in the presence of liquid water. Opportunity found the hematite within days. Embedded in the sedimentary rock were small spherical formations, a few millimeters across, that the team quickly nicknamed blueberries. Hematite concretions formed when iron-rich water percolated through sediment and precipitated out around a nucleation point. The same structures form in certain rock formations in Utah. On Earth, they are unremarkable. On Mars, in 2004, they were the clearest direct evidence yet that liquid water had once stood on the surface. Not just passed through briefly, but persisted long enough to alter the chemistry of the rock from the inside out. Opportunity drove for 15 years. It was never designed to detect life. But the geological case it built, along with Spirit's findings in the Columbia Hills, where hydrothermal minerals suggested ancient hot springs, shifted the central question. Not, was Mars ever wet? That was answered. But, was it wet long enough and in the right chemical conditions to support life? Curiosity landed in August 2012 in Gale Crater, and it was the first rover explicitly designed with habitability assessment as a primary mission goal. Not, is there life? That question was still considered too large for a single mission. But, could life have existed here, given what the chemistry and geology show? The answer it returned, within its first year, was yes. Gale Crater had been a lake. The water had been neutral in pH, not acidic, not highly alkaline. The chemical energy sources that microbes use on Earth were present. The environment had been, by every measure scientists applied, habitable. Between each mission, between each answer that opened into two more questions, Mars kept its silence, as it always has. Perseverance arrived on February 18, 2021, carrying something no previous Mars rover had. A set of instruments and a sample caching system designed not just to assess habitability, but to look directly for biosignatures, and to preserve whatever it found in sealed titanium tubes for eventual return to Earth, where laboratories with capabilities no rover could carry would have their turn. It was the first step in a two-mission chain. The first time the question was asked not just in passing, but with the full weight of a planned answer. The announcement came on June 7, 2018, and NASA, to its credit, did not oversell it. The press release was careful. The language was measured. The scientists who spoke at the briefing chose their words the way you choose your footing on uncertain ground, deliberately, testing each step before committing weight to it. And yet, underneath the carefulness, something was present that hadn't quite been present before. A particular quality of attention. The kind that gathers in a room when people are looking at something they don't fully know how to talk about yet. What Curiosity had found in mudstone samples drilled from a site called Mojave 2 on the slopes of Mount Sharp inside Gale Crater were complex organic molecules. Not simple ones, not just methane or carbon dioxide, which Mars had already yielded. Complex ones, thiophene, benzene, toluene, small aliphatic carbon chains. Molecules built from multiple carbon atoms bonded in rings and branches. The kind of structural complexity that organic chemistry produces when it has time and energy and the right starting ingredients. The scientist who led the analysis was Jennifer Eigenbrod, a biogeochemist at NASA's Goddard Space Flight Center in Maryland. She had spent years working on the data before the announcement, not because the findings were unclear, but because the team was determined to rule out every alternative explanation they could think of before saying anything publicly. That process took the better part of 3 years. The instrument responsible was called SAM, the Sample Analysis at Mars Unit. It works by heating powdered rock samples to very high temperatures, releasing gases that are then sorted and identified by a mass spectrometer. The technique is powerful and well understood. It is also, and this matters, a technique that can introduce complications. Heating certain minerals can generate organic compounds that weren't present in the original sample, through reactions that occur inside the instrument itself during analysis. The team knew this. They had spent considerable effort designing protocols to account for it and modeling what instrument-generated contamination would look like chemically. What they found at Mojave 2 didn't match the contamination profile. The organics were real and they were in the rock. The mudstone they came from was approximately 3.5 billion years old, formed at the bottom of an ancient lake during a period when Gale Crater held standing water. The organics had survived, partially degraded, chemically altered by billions of years of radiation and oxidation, but structurally present, in a geological context that suggested they had been buried quickly after formation and protected from the worst of Mars's surface chemistry. Eigenbrod was precise in her public statements. Organic molecules, she explained, are the carbon-based building blocks associated with life, but they are not exclusive to life. They form through abiotic processes too. Meteorite impacts deliver organic compounds to planetary surfaces. Ultraviolet radiation can drive organic synthesis in thin atmospheres. Volcanic systems produce complex carbon chemistry without any biological involvement. Finding organics in Martian rock did not, by itself, mean life. What it meant was this: the raw chemical ingredients were there. The building blocks existed on ancient Mars in a geological setting consistent with habitability. Whatever happened next, whether chemistry crossed the threshold into biology or not, had the materials it would have needed. That was already more than anyone had been able to say with certainty before. But the organic molecules were not the most puzzling thing Curiosity found in Gale Crater. That distinction belonged to something in the air above it. Across multiple Martian years of operation, Curiosity's SAM instrument had been periodically sampling the atmosphere and measuring methane concentrations. The background level was low, around 0.4 parts per billion, already higher than models of abiotic Martian chemistry predicted it should be. But the background wasn't what drew attention. What drew attention was the variability. The methane concentration rose in Northern Hemisphere summer and fell in winter, cycling with the seasons in a pattern that no purely geological source had cleanly explained. And interspersed with that seasonal rhythm were spikes, sudden, short-lived surges that appeared and disappeared over the course of a few days. The largest spike Curiosity recorded was in June 2019, 21 parts per billion, roughly 10 times the background level. There one day, gone the next. Nobody, as of the time this script was written, has fully explained it. There are places in the universe where the nearest galaxy is a faint smear of light so distant that it offers no warmth, no navigation, no sense of being anywhere in particular. This is one of them. The void between galaxy clusters is not empty in the technical sense. A few stray hydrogen atoms drift through every cubic meter, too sparse to interact, too isolated to form anything. But it registers as empty. It feels, in whatever way a place can feel, like the physical expression of the word nothing. The temperature here is 2.7 Kelvin, just above absolute zero, the faint residual warmth of a universe that was once very hot and has been cooling ever since, spreading its heat across an expanding volume of space for nearly 14 billion years. What remains is this: a cold so complete and so evenly distributed that it barely qualifies as temperature at all. More like the memory of warmth, the final attenuated echo of a beginning. No star casts a shadow here. No planet catches light and holds it. The cosmic microwave background radiation passes through in every direction simultaneously. Ancient, even, undisturbed. It does not illuminate, it simply exists, as it has existed since the universe was 380,000 years old and first became transparent enough for light to travel freely. The nearest large structure is a dim smudge in one direction, a galaxy cluster, millions of light years away, receding slowly as space itself expands between here and there. Everything moves apart from everything else. Not dramatically, not with any urgency, just steadily, gently, the way all things eventually find their distance from each other, given enough time. Here, there is nothing to hold the mind, nothing to name, nothing to count or measure or reach toward. Only the slow expansion of space itself, patient as breathing, carrying everything outward into a quiet that has no edge and no end. Methane should not persist on Mars. That is the starting point for understanding why the Curiosity readings matter as much as they do. The Martian atmosphere is thin, less than 1% the density of Earth's at sea level, and it offers almost no protection from the sun's ultraviolet radiation. UV light breaks molecular bonds. On Mars, it tears apart complex molecules at the surface and in the lower atmosphere with a thoroughness that Earth's ozone layer spares us from entirely. Methane, under those conditions, has a calculated atmospheric lifetime of somewhere between 300 and 600 years. In geological terms, that is essentially instantaneous. For methane to be present in the Martian atmosphere at all, something must be producing it now. Or recently enough that now and recently are the same word at this scale. The background level Curiosity measured, around 0.4 parts per billion, was already higher than models predicted for a geologically quiet Mars with no active methane source. Atmospheric scientists had theories about where it might come from, none of them fully satisfying. Then the seasonal signal emerged from the data, concentrations rising through northern hemisphere summer, peaking, then declining through winter. A rhythm, predictable enough to plan around, strange enough to resist easy explanation. Then the June 2019 spike, 21 parts per billion, recorded over several consecutive days before dropping back toward baseline. The Curiosity team, led at that point by Chris Webster at NASA's Jet Propulsion Laboratory, had been watching for anomalies like this for years. Webster's group published the finding in the journal Nature Geoscience in 2019. They were careful to present all three possible explanations with equal weight. The first is geological. A process called serpentinization occurs when water interacts with certain iron and magnesium-rich silicate rocks, olivine in particular, producing hydrogen gas and, under some conditions, methane. This happens on Earth too, including at mid-ocean ridges and in certain ophiolite complexes where ancient oceanic crust has been exposed at the surface. Mars has abundant olivine. If liquid water still exists somewhere in the subsurface, which, as we'll come to later, is a genuinely open question, serpentinization could be producing methane in pockets and releasing it through cracks in the rock when pressure builds sufficiently. The seasonality might reflect thermal expansion and contraction of surface rock, opening and closing those pathways. The second explanation is simpler and less interesting. The methane was never atmospheric in origin. It was adsorbed, chemically bound to the surface of soil grains, and was being released as surface temperatures rose in summer. A kind of slow outgassing from the regolith rather than active production. This would explain the seasonal pattern without requiring any ongoing chemistry. It would not, however, explain the magnitude of the June 2019 spike, which was too large and too sudden to fit neatly with a simple adsorption-desorption model. The third explanation is biological. On Earth, approximately 90% of atmospheric methane is produced by living organisms, primarily methanogens, a group of microorganisms that produce methane as a metabolic byproduct of consuming hydrogen and carbon dioxide. They are among the most ancient life forms on Earth, capable of surviving in anoxic environments, in extreme temperatures, deep underground, in conditions that would kill most other organisms. If anything analogous existed on Mars, in the subsurface, in liquid water pockets kept warm by residual geothermal heat, the methane signature would look, from the surface, something like what Curiosity has been measuring. Nobody is claiming that. The biological hypothesis sits at the end of the list, behind two abiotic alternatives that are at least partially supported by known Martian geology. But it sits on the list. What complicated the picture further was what happened in September 2019, when a reanalysis of data from the European Space Agency's Mars Express orbiter was published. Mars Express had been orbiting Mars since 2004, carrying a spectrometer called the Planetary Fourier Spectrometer. On June 16, 2013, the day after one of Curiosity's elevated methane readings from the surface, Mars Express had detected a methane spike from orbit. The orbital detection independently corroborated a surface measurement from a completely different instrument on a completely different spacecraft operated by a completely different agency. That matters. It rules out instrument error on Curiosity's part. Whatever produced the signal was real enough to appear in two independent data streams simultaneously. Then the Trace Gas Orbiter arrived. Launched in 2016 as a joint mission between the European Space Agency and Russia's Roscosmos, the Trace Gas Orbiter was designed specifically to map trace gases in the Martian atmosphere, including methane, with sensitivity far exceeding any previous instrument. It began science operations in 2018. Its results were, to put it mildly, confusing. The TGO detected methane, but at levels far below what Curiosity had been measuring from the surface. Where Curiosity found 0.4 parts per billion as a background and spikes up to 21, the TGO found something closer to 0.05, near the edge of its detection limit, inconsistently, without the seasonal pattern the surface readings showed. The discrepancy has not been resolved. The two datasets are difficult to reconcile without invoking processes, very localized methane sources, very rapid atmospheric destruction mechanisms, that themselves require explanation. Several papers have proposed models. None has achieved consensus. This is not a failure of science. It is science doing exactly what it should do, accumulating data that doesn't fully agree, resisting premature resolution, staying with the discomfort of genuine uncertainty until better instruments or better models earn the right to close the question. While that argument continued in journals and conference rooms, a different group of scientists had turned their attention away from the atmosphere entirely. They were looking down, at the oldest rocks in Jezero Crater, at what the minerals themselves had to say. The methane debate is, at its core, a present tense argument. Something is producing that gas now, or recently enough to matter, and the argument is about what. But while atmospheric scientists worked through the data from Curiosity's SAM instrument, A parallel investigation had been running for years in a completely different discipline, using completely different tools, asking a question that wasn't about what Mars is doing now, but about what Mars recorded in its rocks a very long time ago. Geologists, working with spectral data from orbiters, had been building a mineralogical portrait of ancient Mars, not just where the water was, but what kind of water, for how long, in what chemical environment, interacting with what rock types. The picture that emerged was not the simple wet then dry story that early missions had suggested. It was more complicated, and in some ways, more interesting. The instrument that made most of this possible was CRISM, the Compact Reconnaissance Imaging Spectrometer for Mars, aboard NASA's Mars Reconnaissance Orbiter, which has been circling Mars since 2006. CRISM reads the spectrum of sunlight reflected from the surface in 544 distinct wavelength channels, from ultraviolet through near-infrared. Different minerals absorb and reflect different wavelengths in characteristic patterns, spectral fingerprints that allow identification from orbit with a spatial resolution of about 18 meters per pixel. What CRISM found at Jezero Crater, over years of targeted observation, changed the mission profile of what would become Perseverance. It found carbonates, minerals that form when carbon dioxide-rich water interacts with calcium and magnesium over long periods, under conditions that on Earth are associated with shallow, biologically productive lakes. It found olivine in the surrounding terrain, consistent with ancient volcanic activity. And along the ancient shoreline of the Jezero Lake, it found a mineral assemblage that told a specific story about chemistry and time. The delta fan at the northern rim of the crater, where an ancient river had met the lake and deposited its sediment load, became the primary target. Not because it was the most accessible or the most visually dramatic, but because on Earth, river deltas are where organic material concentrates and gets buried fast, protected from oxidation by rapid sediment accumulation. If anything organic had existed in or near that ancient Martian lake, the delta was where it would have been carried, deposited, and sealed. Perseverance reached the delta in April 2022, after spending its first year on the crater floor. What it found there, in a specific mudstone outcrop the team named Wildcat Ridge, is where all of these threads converge. There's a patience to this story. Layer by layer, instrument by instrument, year by year. If you've been with us this long into the night, you're exactly the kind of person this channel was built for. A like helps more people find their way here when sleep is hard to come by. And subscribing means there'll be something waiting the next time the night gets quiet and you need somewhere to go. Now, back to Wildcat Ridge. The decision to send Perseverance to Jezero Crater was not unanimous. There were 47 candidate landing sites considered over 3 years of workshops, debates, and analysis. Each one had advocates, each one had problems. Jezero had its own. The delta fan created a terrain of ridges and boulders that made landing difficult, and the scientific case for it rested heavily on orbital data that had never been ground truth by a rover. You can read a mineral signature from orbit. You cannot be certain from orbit alone what that mineral means in context. NASA landed there anyway on February 18, 2021, at 3:55 p.m. Eastern Time, after the now famous 7 minutes of terror, during which the spacecraft decelerated from 12,000 miles per hour to a complete stop using a sequence of parachutes, retro rockets, and a sky crane system that lowered the rover on cables to the surface. The entry, descent, and landing team at JPL sat in near silence through the whole sequence. When confirmation came, the signal delayed by the 11 minutes it takes light to travel from Mars to Earth, the room released something it had been holding for a long time. The rover spent its first months on the crater floor in a formation the team called Maz, a Navajo word for Mars. The rocks there were igneous, volcanic in origin, crystallized from ancient lava. Not ideal for biosignature preservation, volcanic rocks don't tend to concentrate and protect organic material the way sedimentary ones do, but scientifically valuable. The igneous rocks allowed precise radiometric dating that helped establish the timeline of Jezero's geological history. Then, in the spring of 2022, the rover drove north toward the delta. The approach to the Delta Scarp, a roughly 40-meter cliff of layered sedimentary rock, was, by rover standards, dramatic. Each layer in that cliff face represented a period of deposition. Each period told something about the conditions in the lake at that time: the water chemistry, the sediment source, the rate of accumulation. The team identified their primary target, a fine-grained mudstone unit at the base of the delta sequence, laid down in the deepest, quietest water, where the finest particles, the ones most likely to carry and preserve organic material, had settled. They called it Wildcat Ridge. On July 20th, 2022, 46 years to the day after Viking 1 touched down on Mars, Perseverance drilled its first sample from Wildcat Ridge. The sample was sealed into titanium tube number 266, stored in the rover's belly, and added to the growing cache of material that represents humanity's most careful attempt yet to bring a piece of Mars home. The instrument that analyzed it in place, before caching, was Sherlock, the scanning habitable environments with Raman and luminescence for organics and chemicals. It works by firing a deep ultraviolet laser at the rock surface and measuring the light that scatters back. Different molecular bonds scatter light at different characteristic frequencies, a technique called Raman spectroscopy, allowing identification of specific compounds without any need to heat or dissolve the sample. It is, by design, a gentler and more chemically specific tool than anything Curiosity carries. The lead scientist on Sherlock's operations was Dr. Sunanda Sharma, a researcher at NASA's Jet Propulsion Laboratory who had spent years developing the instrument's detection algorithms and calibration protocols. When Sharma's team processed the Wildcat Ridge data, the spectra showed organic signals, not ambiguous traces at the edge of detection, but clear, reproducible peaks corresponding to aromatic ring compounds and aliphatic carbon chains. More than the molecules themselves, it was their setting that stopped people. They were embedded in a carbonate silica mineral matrix, precisely the combination that CRISM had predicted from orbit, now confirmed on the ground. Carbonates and silica, together in a fine-grained lake sediment. And within that matrix, organics in concentrations and structural types that in every terrestrial geological context ever studied are most abundantly produced by one thing. The team published their preliminary findings in Science in 2023. The word they chose, with full awareness of its weight, was consistent. Consistent with biological processes. Not proof, not confirmation. The study was explicit that abiotic pathways could not be ruled out. But the full picture, the molecule types, their concentrations, the mineral context, the depositional environment, the age of the rock, assembled itself into a pattern that the authors described as warranting serious consideration of a biological origin. Several of the scientists involved had been working on Mars biosignature research since before Curiosity launched. They had seen false positives. They had written papers about the risks of overinterpretation. They were not people inclined toward wishful thinking. And yet, the data sat in front of them, and the pattern was what it was. And the most parsimonious explanation, the one that required the fewest additional assumptions, was one that, a generation ago, would have been career-ending to say out loud at a NASA press conference. 3 threads. Hold them together for a moment. Organic molecules, thiophenes, benzene, toluene, complex carbon chains. preserved in 3.5 billion-year-old mudstone at the bottom of an ancient Martian lake. Detected by an instrument designed specifically to avoid the ambiguities that plagued earlier findings. Real, reproducible, in the rock. Methane fluctuating in the Martian atmosphere in patterns that geological models strain to account for. A June 2019 spike of 21 parts per billion, confirmed independently by 2 spacecraft from 2 different agencies on 2 different days. Present, unexplained, still there in the data, waiting. And now, at Wildcat Ridge, aromatic organics embedded in a carbonate silica matrix in a fine-grained lake sediment, a combination that terrestrial geology associates overwhelmingly with biological processes. Described by the scientists who found it not as a curiosity, not as an artifact, but as consistent with life. Each thread individually has abiotic explanations that remain viable. The combination is harder. Scientists are trained rigorously, professionally, by years of methodology and peer review to resist the pull of converging evidence, to hold each line of data separately and evaluate it on its own terms, to resist the mind's natural tendency to see a pattern and decide the pattern means something. That discipline is not a weakness. It is what makes science trustworthy. But there are moments when even the most careful scientists find themselves doing the arithmetic anyway, quietly, not in print, in the particular silence of a late night in an office with the data on the screen and no one watching. In 2022, analyzing the Wildcat Ridge spectra, some of them did the arithmetic. What the numbers suggested, not proved, suggested, was something that every Mars scientist has been circling for 50 years without being able to say cleanly. And the reason it landed the way it did, in that room, in those minds, wasn't just the data itself. It was that this time, the data was designed to be hard to argue with. Consider what the lake was, not a metaphor, an actual lake, water standing on the surface of Mars, liquid water covering the floor of a crater 45 kilometers wide, fed by a river that drained a catchment area spanning hundreds of kilometers of ancient volcanic highland. The water was there long enough, geologists estimate tens of thousands of years at minimum, possibly much longer, to deposit the sediment layers we can read today in the Wildcat Ridge outcrop. Long enough for the lake chemistry to reach a kind of equilibrium. Long enough for the fine silt carried in from the highlands to settle, grain by grain, to the bottom. The water was not pure. It was mineral-rich, slightly alkaline, laced with dissolved calcium and magnesium carbonates leached from the volcanic rock of the surrounding terrain. On Earth, this chemistry, alkaline, carbonate-buffered, mineral-rich, describes environments like Mono Lake in California or the soda lakes of East Africa's Rift Valley. Both are among the most biologically productive environments on the planet. Both host dense microbial communities that thrive in conditions most organisms find inhospitable. That is not coincidence. It is chemistry. The temperature at the surface of that Martian lake 3.7 billion years ago was almost certainly near or below freezing on average. Mars was already losing its magnetic field, already beginning the slow atmospheric thinning that would eventually leave it the cold, dry world it is today. But near freezing is not below freezing. And in the shallow margins of the delta, where sunlight warmed the sediment and geothermal heat from the still active Martian interior may have warmed it further, conditions could have been considerably milder. And there was energy, chemical energy, the kind that doesn't require sunlight at all. The volcanic minerals in the surrounding rock, olivine, pyroxene, react with water to produce hydrogen. Hydrogen is fuel. On Earth, entire ecosystems in the deep ocean run on hydrogen produced by the interaction of seawater with volcanic rock, in complete darkness, miles below the surface. These hydrothermal vent communities have no relationship to sunlight. They are powered by chemistry alone, by the slow, patient reactions of water and rock, and they have been running continuously for as long as the Earth has had liquid water on it. The chemistry at Jezero, during its wet period, would have supported the same reaction. So when the Wildcat Ridge sediment was accumulating, when silt was settling through that slightly alkaline, mineral-laden water and being buried quickly enough to protect whatever it carried, the environment it was recording had water, chemical energy, the right mineral matrix, the right temperature range, and now, in the Sherlock data, organic molecules of a type and in a context that, in every analogous terrestrial setting ever studied, from the ancient cherts of Western Australia to the carbonate silica deposits of Yellowstone's hydrothermal pools, from the lake sediments of East Africa to the deep sea sediments of the Atlantic floor, from the most ancient rocks on Earth that still carry any chemical record at all, down to the freshest lake mud sampled last year by a graduate student pulling a core, has one explanation that accounts for the full pattern more simply and more completely than any other explanation that has ever been seriously proposed. In the summer of 2022, Sunanda Sharma's team at JPL published their analysis of the Wildcat Ridge Sherlock data in the journal Science. The finding stated plainly, aromatic organic compounds, including ring-structured molecules consistent with the degradation products of biological material, detected within a carbonate silica matrix in a fine-grained lacustrine mudstone approximately 3.5 billion years old. Lacustrine means lake-formed. The word matters. These were not surface deposits exposed to Mars's oxidizing chemistry and ultraviolet radiation. They were bottom sediments, buried quickly, sealed by subsequent layers, preserved in the one geological environment on Mars most analogous to the environments on Earth where ancient biological signatures have been found most reliably. The specific compounds Sherlock detected included polycyclic aromatic hydrocarbons, PAHs, a class of molecules built from multiple fused benzene rings. PAHs form abiotically through combustion and through certain high-temperature chemical reactions. They arrive on planetary surfaces via meteorite impacts. They are, on their own, not proof of anything biological. But the PAHs at Wildcat Ridge were not on their own. They were found alongside aliphatic organic compounds, long carbon chains of the type that form the structural backbone of biological lipids, the molecules that build cell membranes. And they were found within a carbonate silica mineral matrix whose chemistry, as Sharma's team noted carefully in the paper, is consistent with the mineral assemblages produced by microbial mat communities in shallow lacustrine environments on Earth. On Earth, this combination, PAHs, aliphatic organics, and carbonate silica minerals in lake sediment, is not something that occurs routinely through abiotic processes. It occurs in settings where biology has been present, where organisms have lived, died, been buried, and left their molecular remains in the rock. In the language Sharma used, the pattern was consistent with biological processes. That phrase carried more weight than it appears to on first reading. Astrobiologists don't deploy consistent with biological processes as a hedge or a throwaway qualification. They use it when they mean, we have looked for an abiotic explanation that accounts for the full pattern, the molecule types, the relative concentrations, the mineral association, the depositional context, and we have not found one that is fully satisfactory. The biological hypothesis accounts for all of it. The abiotic hypotheses account for parts of it. Sharma said in an interview following the publication that the team had run extensive laboratory comparisons, measuring what Fischer-Tropsch synthesis and UV-driven organic chemistry and meteorite-delivered organics actually look like in carbonate silica matrices, and that none of the abiotic profiles matched the Wildcat Ridge spectra as closely as the profiles produced by degraded biological material. She was careful. She did not say life. She said consistent with. But she also said this, that if these samples were found in a rock formation on Earth, in an ancient lake deposit from the Archean era, the scientific community would accept the biological interpretation as the working hypothesis pending further analysis. The reason the bar is higher for Mars is not that the data is weaker. It is that the implications are larger. That is not a small thing to say. There is a version of this story that would be easier to tell. In that version, NASA holds a press conference. A scientist stands at a podium and says the word. The word travels around the world in seconds. Every question humanity has carried about its place in the universe resolves cleanly into an answer. We are not alone. We were never alone. Something lived on Mars. That version is not this version. What we have instead is harder and, in its own way, more interesting. We have data that a careful, skeptical, thoroughly credentialed group of scientists have examined from every angle they can think of, tested against every alternative explanation they could construct, and concluded, not unanimously, not without reservation, but genuinely, that the biological hypothesis fits better than anything else currently on the table. Consistent with is scientific language for we cannot rule it out and we cannot find anything that explains it more simply. Consider what that actually requires. To say that a set of findings is consistent with biological processes, you first have to eliminate the alternatives. You have to ask, could Fischer-Tropsch synthesis produce this? Could meteoritic delivery account for it? Could UV-driven organic chemistry in the ancient atmosphere explain the concentrations and the compound types? Could hydrothermal circulation, without any biological component, produce this specific mineral-organic association in this specific depositional context? You ask each question rigorously. You build the laboratory analogs. You run the models. You write the papers. And then, after all of that, if the biological explanation still fits better, if it still accounts for the full pattern more cleanly than any of the alternatives, you say, consistent with. You do not say, proof. You do not say, confirmed. You say the most honest thing the data allows. Think of it this way. Imagine finding, on a distant world, a rock that has been worn smooth on one side, with a groove running lengthwise along it, and traces of a material embedded in the groove that matches no known mineral, but closely resembles a specific organic compound. Each feature has a natural explanation. Rocks get worn smooth by water. Grooves form through differential erosion. Organic compounds arrive via meteorite. But the combination, smooth, grooved, organic bearing, in a context where flowing water was present, starts to suggest something that wasn't random. You wouldn't call it proof. You would call it consistent with use by a tool-bearing organism. And you would not stop looking. Mars kept its silence, as it always has. But silence, examined closely enough, has a texture. And the texture of Wildcat Ridge is not what an empty planet looks like. The uppermost layer is almost white, Ammonia crystals suspended in thin, cold air at the top of a world that has no surface, no ground, no bottom, only depth. The crystals catch the light of a distant sun and scatter it in all directions at once, so that the whole upper atmosphere glows faintly, evenly, like the inside of a paper lantern. The light here is thin, the sun is far, but it reaches. Below this layer descending, the color shifts. Pale cream first, a softening of the white, a warming of it, as the temperature rises by a degree, then 2, then 10. The pressure increases not dramatically, but continuously, the way depth in water increases. A gentle, even weight, not uncomfortable. Something closer to the feeling of a heavy blanket, or of being held still by something larger than yourself. Deeper. The cream deepens to amber, a rich, old amber, the color of late afternoon light through drawn curtains. The clouds here are not the wispy, scattered things of the upper atmosphere. They are dense, layered, slow-moving in long bands that stretch around the entire circumference of the planet. Currents the width of continents, moving at speeds that would tear apart anything not built for them. And yet, from inside, they appear almost still. The scale is so large that motion becomes invisible. A cloud deck the color of old copper passes below, and below that, something flickers. Lightning. Not the sharp, violent lightning of a terrestrial thunderstorm, something slower, more diffuse, lighting up the interior of a cloud from within, like a thought moving through a mind half asleep. It pulses once, twice, then is quiet for a long time, then pulses again. A rhythm with no urgency to it, a heartbeat measured not in seconds, but in minutes. Deeper still, the amber darkens. The pressure is significant now, several times what it was at the entry point, but it increases so gradually that there is no single moment of transition, only the continuous, gentle fact of it, like the slow accumulation of a very long time. The temperature is rising. The cold of space feels very far away. There is no surface coming, no ground to reach. The gas simply grows denser and warmer and darker, and the distinction between gas and liquid becomes theoretical rather than actual. A boundary that exists in physics textbooks, but not in any place you could point to. The lightning is gone now above. The white layer is gone. There is only the dark amber pressing in from all sides, warm and total, and the slow, deep hum of a world that has been this way for 4 billion years and will be this way for 4 billion more. No destination, no urgency, only downward and warmer and quieter and slower, until the idea of somewhere else becomes difficult to hold, and the amber dark is simply everything there is, and everything there is still. On August 7th, 1996, Bill Clinton stood at a podium outside the White House in the early morning and made a statement that no sitting American president had made before or has made since. Today, he said, Rock 84001 speaks to us across all those billions of years and millions of miles. The rock in question had been lying in the Allen Hills region of Antarctica since approximately 13,000 years ago, when it landed after a journey that had taken it from the surface of Mars, through interstellar space, through Earth's atmosphere, and onto an ice field at the bottom of the world. A geologist named Roberta Skor found it during a 1984 field expedition, collected it in a bag, assigned it the catalog number ALH 84001, and sent it to the Johnson Space Center in Houston, where it sat in storage for 9 years before anyone realized what it was. The identification came in 1993, when a researcher named David Mittelfeld noticed that the rock's oxygen isotope ratios didn't match any known terrestrial or lunar geology. They matched precisely the atmospheric signature of Mars, a signature established by the Viking landers 17 years earlier, locked into gas bubbles trapped inside the rock during the impact that ejected it from the Martian surface roughly 17 million years ago. ALH 84001 was 4.1 billion years old, older than any rock ever found on Earth's surface. It had formed during the Noachian period, the same era as the Wildcat Ridge sediments, when Mars was warm, wet, and, based on everything we now know, habitable. The team that studied it, led by David McKay at NASA's Johnson Space Center, spent 3 years building their case before going public. What they presented in August 1996, in a paper published in Science, was a 4-pronged argument, 4 independent lines of evidence, each one individually explicable by non-biological processes, but which together, they argued, constituted a biosignature case that deserved serious consideration. The first was the presence of polycyclic aromatic hydrocarbons, PAHs, concentrated in the interior of the meteorite, away from the outer surfaces where terrestrial contamination was possible. The same class of compounds that Sherlock would detect at Wildcat Ridge 26 years later. The second was the presence of carbonate globules, small disks of carbonate mineral, a few hundred micrometers across, with a distinctive banded structure and chemical zoning that McKay's team argued was more consistent with biological precipitation than with purely inorganic carbonate formation. The third was magnetite crystals, tiny particles of iron oxide found within the carbonate globules, whose size, purity, and crystal structure closely resembled the magnetite produced by magnetotactic bacteria on Earth. These are microorganisms that synthesize magnetite crystals internally, using them as tiny biological compasses to navigate along Earth's magnetic field. The magnetite in ALH 84001 was unusually pure, unusually small, and unusually well formed for an inorganic origin. The fourth was the structures themselves. Under high-resolution electron microscopy, the carbonate globules contained elongated, segmented features, roughly 20 to 100 nanometers long, that McKay's team described as possible nanofossils, the mineralized remains of ancient microbacteria. They were smaller than any bacteria known on Earth at the time, which immediately drew criticism, but their shape and arrangement were striking. Clinton's press conference followed the Science publication by a matter of hours. The scientific counterattack began almost immediately. Within weeks, competing teams were picking apart each of the 4 lines of evidence. The PAHs could be terrestrial contamination. The meteorite had been sitting in ice for 13,000 years, and PAHs are ubiquitous in Antarctic environments. The carbonate globules could form abiotically at high temperatures through impact-related processes. The nanofossil structures were too small to contain the minimum molecular machinery of a living cell, and similar shapes had been produced in purely inorganic laboratory experiments. The magnetite argument was the most durable. Several subsequent papers confirmed that the crystal morphology and chemistry of the ALH 84001 magnetite was genuinely unusual and difficult to fully explain without a biological component. But even that was not universally accepted. By the early 2000s, the scientific consensus had shifted against the McKay team's interpretation. Not violently, not dismissively. The debate remained technically alive in the literature, but the majority position was that each of the 4 lines of evidence had a plausible abiotic explanation, and that the case for biology, while not disproved, had not been convincingly made. Kathy Thomas Caperta, one of the key scientists on the original McKay team, continued publishing on the magnetite question for 2 decades. As recently as 2009, her group published a paper arguing that approximately 27% of the magnetite crystals in ALH 84001 had no known abiotic formation pathway, that the only process known to produce magnetite with exactly those characteristics was a biological one. The paper did not settle the debate, but it didn't go away either. What ALH 84001 accomplished in the end was not a discovery, it was a curriculum. It taught a generation of astrobiologists exactly what a weak biosignature case looked like, what the failure modes were, where the alternative explanations crept in, how to structure a multi-line argument so that the weaknesses of each individual piece were acknowledged rather than papered over. The scientists who designed Sherlock, who specified the mineral context requirements for a credible biosignature detection, who chose Jezero Crater partly because its carbonate silica chemistry matched the most defensible terrestrial biosignature contexts on Earth, many of them had spent years working through the ALH 84001 debate and drawing specific technical lessons from it. When Sunanda Sharma's team described the Wildcat Ridge findings as consistent with biological processes, they were using a phrase whose meaning had been sharpened by 30 years of post-ALH 84001 argument into something considerably more precise than it sounds. They knew exactly what they were saying, and they said it anyway. The rocks here move, but you would not know it to look at them. Each one follows its own path around the sun, a long, slow ellipse traced and retraced over millions of years, unchanged since the solar system settled into its current arrangement and left these fragments here, uncollected, between the inner and outer planets. They are the material that never became a world. The pieces that came close, perhaps, and then drifted apart again before gravity could gather them into something larger. One of them tumbles slowly as it goes, not dramatically, a fraction of a degree per second, a rotation that takes many hours to complete. Sunlight at this distance is warm but thin, arriving at perhaps a third the intensity it has at Earth, and the rock catches it at a different angle with each slow turn. The illuminated face glows a dull rust orange, threaded with veins of pale olivine crystal that catch the light and hold it for a moment before the rotation carries them back into shadow. The shadow side is very dark. Another rock drifts past at a distance, close by the standards of this region of space, which means several hundred kilometers. Its surface is pocked with small impact craters, each one a record of a collision that happened in silence, in the dark, at some point in the last 4 billion years. The craters do not look fresh. Nothing here looks fresh. Everything has the quality of great age, of having arrived at its current state through a process so long and so gradual that the word process barely applies. The silence is complete. Not the silence of a room where sound might arrive at any moment, but the silence of a place where sound has no medium to travel through and never has. The silence of objects that have been moving, undisturbed, in their slow orbits since before anything on Earth was alive to name them. One of these rocks, pulled by a small gravitational perturbation some millions of years from now, will begin a new path, a longer ellipse, an approach to the inner solar system, a closer path to the sun. But that is millions of years from now, and for now it continues as it has always continued, dark on one side and faintly lit on the other, tumbling its slow, patient tumble through a silence that asks nothing of it and requires nothing in return. The case for ancient Martian life is not the only case the data supports. That's not a caveat offered reluctantly or a legal disclaimer appended to protect the channel from criticism. It's the honest state of the science, and the scientists most deeply invested in the biological hypothesis would be the first to say so. The abiotic explanations deserve the same careful treatment as the evidence that challenges them. Not because they're equally likely necessarily, but because intellectual honesty about what we don't know is the only thing that makes the evidence we do have worth anything. So, the alternative explanations laid out fairly. The organic molecules in the Gale Crater mudstone, the thiophenes, benzene, toluene, and aliphatic chains detected by Curiosity's SAM instrument, have a well-documented abiotic origin pathway. It's called Fischer-Tropsch synthesis, and it occurs when carbon monoxide and hydrogen gas react under heat and pressure in the presence of certain metal catalysts. The reaction was discovered in the 1920s by two German chemists, Franz Fischer and Hans Tropsch, and it produces exactly the kinds of complex organic molecules that SAM found. Mars has the starting ingredients: volcanic CO, hydrogen from serpentinization reactions, iron and nickel catalysts in the basaltic rock, and the ancient hydrothermal environments associated with volcanic activity would have provided the heat and pressure the reaction requires. This is not a theoretical possibility invented to explain away inconvenient data. Fischer-Tropsch chemistry has been observed operating in terrestrial hydrothermal systems, in meteorites, and in laboratory simulations of early planetary conditions. It is real, it is well understood, and it produces organic compounds that look, chemically, very similar to what Curiosity detected. The methane seasonality has its own abiotic candidate. Serpentinization, the reaction between liquid water and iron magnesium silicate minerals, primarily olivine, produces both hydrogen and methane as direct products. Mars has abundant olivine, particularly in the ancient volcanic highlands of the southern hemisphere. If liquid water exists anywhere in the Martian subsurface today, and there are reasons to think it might, which we'll come to, serpentinization could be actively producing methane and releasing it through fractures in the rock. The seasonality of the surface signal might reflect the thermal expansion and contraction of near-surface rock opening and closing those fracture pathways as temperatures change with the seasons. This explanation has genuine supporting evidence. Serpentinization-driven methane has been directly measured in terrestrial geological settings. The Lost City hydrothermal field on the Mid-Atlantic Ridge, for instance, where the seafloor is actively producing methane from olivine water reactions without any biological involvement whatsoever. The chemistry is well characterized. The rates of production are measurable. The hypothesis is not a placeholder. The Wildcat Ridge carbonate-silica organic association is harder to fully account for abiotically, but not impossible. High-temperature hydrothermal fluids moving through carbonate-forming environments can precipitate both silica and carbonates simultaneously, and those fluids carry dissolved organic compounds delivered by meteorite impacts over the course of Mars's history. The early solar system was rich in carbonaceous chondrites, meteorites containing complex organic molecules including amino acids and PAHs, and Mars received its share of them. If those meteorite-delivered organics were dissolved into hydrothermal fluids and then co-precipitated with carbonate and silica minerals, the resulting rock could, in principle, show a mineral-organic association that superficially resembles what biology produces. In principle. Here is where the abiotic case develops its difficulties, and where intellectual honesty requires acknowledging them as clearly as the abiotic alternatives themselves deserve to be presented. Fischer-Tropsch synthesis preferentially produces certain types of organics in certain ratios. Specifically, it produces more straight-chain aliphatic compounds than ring-structured aromatic ones. The Wildcat Ridge sample showed a ratio of aromatic to aliphatic compounds that sits at the high end of what Fischer-Tropsch chemistry typically generates, and at the low end of what biological degradation products typically show. Not definitively outside the abiotic range, but not comfortably inside it either. The seasonal methane signal is consistent with serpentinization, but the magnitude of the June 2019 spike, 21 parts per billion in a single measurement, dropping back to near background within days, is difficult to account for through serpentinization rates calculated from known olivine abundances and estimated subsurface water availability. Serpentinization tends to be a slow, continuous process. Spikes of that size and duration are more consistent with either a sudden release from a pressurized reservoir, which could be abiotic, or with a biological source whose activity fluctuates, which is also consistent with what methanogens do in seasonally varying temperature conditions. And the carbonate-silica organic association at Wildcat Ridge, when Sharma's team ran laboratory simulations of abiotic hydrothermal precipitation using Martian analog chemistry, Martian analog temperatures, meteorite-delivered organic compounds as the carbon source, the spectral profiles they generated did not match the Sherlock data from the actual sample, as well as the profiles generated from degraded biological material. Not impossibly different, not conclusively different. Different enough to note. The honest position, held by most working astrobiologists as of the time this was written, is something like this. The abiotic explanations are viable for each individual piece of evidence. They require no exotic chemistry, no unknown processes, no special pleading. Mars almost certainly has active abiotic organic chemistry operating at some level, and some portion of what the rovers have detected almost certainly reflects that chemistry. What the abiotic explanations have not yet managed to do, collectively, taken together as a package, is account for the full pattern at Wildcat Ridge more simply than the biological hypothesis does. That gap may close. Better laboratory analogs, better atmospheric models, better understanding of Martian subsurface hydrology could fill it. Science is not finished, but the gap is there. And the scientists who know it best are the ones who keep, carefully, not closing the file. 4 billion years ago, Mars and Earth were not the worlds they are today. This sounds obvious stated plainly, but the implications are easy to underestimate. We are accustomed to thinking of Mars as it currently is: cold, thin-aired, radiation-scoured, geologically quiet, and projecting that image backward in time, as though the planet has always been a desert, and we are simply asking whether something once managed to survive there anyway. That framing is wrong. It misrepresents both planets. The early Earth was not the blue, oxygen-rich, biologically saturated world we know. Its atmosphere was largely carbon dioxide and nitrogen, with no free oxygen. That came later, produced by photosynthetic organisms over a timescale of roughly 2 billion years. The surface was volcanically active. The oceans were shallower, the continental land masses smaller and differently arranged. The sky, most days, was not blue, but a pale orange, tinted by methane and haze. Early Mars, at the same moment, was not identical to early Earth, but the differences were smaller than they became. Mars also had a thicker atmosphere, also dominated by carbon dioxide and water vapor. Its surface pressure was higher, perhaps comparable to what you'd experience at several thousand meters altitude on Earth today. Thin, but not the near vacuum of the modern Martian surface. The planet retained a magnetic field, generated by a still active liquid iron core. Not as strong as Earth's, but sufficient to deflect at least some of the solar wind that would later strip the atmosphere away. Volcanic activity was ongoing, replenishing atmospheric gases and driving the hydrothermal chemistry that we've been discussing. The temperatures were cold. Mars is farther from the Sun, and the early Sun was roughly 70% as luminous as it is today. But models suggest that volcanic outgassing and greenhouse warming from carbon dioxide could have kept portions of the surface above freezing, particularly in the lower elevation regions and around volcanic centers. Not warm, not comfortable by any standard a human would recognize, but above freezing, intermittently, in places, for periods long enough to account for the river valleys and lake deposits the orbiters have mapped. Here is the comparison that matters. The oldest potential evidence for life on Earth, carbon isotope signatures in ancient zircon crystals from the Jack Hills of Western Australia, analyzed by a team led by Elizabeth Bell at UCLA and published in 2015, dates to approximately 4.1 billion years ago. The same era as ALH 84001. The same era as the Jezero Lake. The same era as the oldest Noachian terrain on Mars. If that interpretation is correct, and it remains debated, as any claim about 4 billion year-old biosignatures should be, then life arose on Earth under conditions that were, in several important respects, similar to conditions that existed simultaneously on Mars. Similar carbon chemistry, similar liquid water environments, similar hydrothermal activity, similar timescale from planetary formation to potential biogenesis. The implication is not that life definitely arose on Mars because it arose on Earth in similar conditions. The implication is that if the conditions were genuinely similar, and if life arose on one of the two planets in those conditions, the question of whether it arose on the other is not a question of whether the environment was suitable. It's a question of whether the specific chemical event, the origin of self-replicating chemistry, happened twice, in two places, in the same window of time. That question has no answer yet, but it is a different question, and a more specific one, than asking whether Mars could ever have supported life. Two rocky planets, the same billion-year window, similar chemistry, similar water, similar energy sources. One of them we know generated life. The other has molecules in its rocks that the scientists who found them cannot fully explain without it. The arithmetic is uncomfortable in the best possible way. Everything we've discussed so far describes the surface of Mars, or what the surface preserves from a time when conditions were different. The surface today is hostile. There is no softening that conclusion. Ultraviolet radiation at Martian ground level is intense enough to degrade complex organic molecules within hours of exposure. The soil chemistry is oxidizing. Those reactive compounds that confuse the Viking biology results are present across most of the surface, breaking down organic material rather than preserving it. The atmospheric pressure is so low that liquid water cannot exist at the surface under any currently observed conditions. It would either freeze or evaporate instantly. Whatever was once possible on the Martian surface is no longer possible there. But the surface is not Mars. Mars extends downward, kilometers downward, and the deeper you go, the less the surface conditions matter. In July 2018, Roberto Orosei and his colleagues at Italy's National Institute for Astrophysics published a paper in Science reporting a remarkable detection. The MARSIS radar instrument aboard the European Space Agency's Mars Express orbiter, which had been bouncing radio waves off the Martian surface and subsurface since 2005, had detected an anomalously bright radar reflection from a point approximately 1.5 kilometers beneath the South Polar Layer deposits. The reflection had a specific character. the kind of high radar reflectivity that, in terrestrial contexts, is associated with liquid water. The signal suggested a body of liquid water roughly 20 kilometers across, sitting beneath more than a kilometer of ice. The interpretation was immediately debated. Several research groups proposed that the radar signature could be explained by frozen clay minerals or carbon dioxide ice rather than liquid water, materials that can produce similar radar reflections without requiring liquid. The argument has not been resolved. Subsequent analysis has found additional anomalous radar reflections in the same region, which some researchers interpret as multiple subglacial lakes, and which others interpret as further evidence of a complex mineral deposit. Nobody has been able to look directly. The instruments available don't allow it, and no mission currently funded is designed to drill through 1.5 kilometers of Martian polar ice. But the possibility is not dismissed. And on Earth, the discovery of Lake Vostok, a liquid lake the size of Lake Ontario sitting beneath nearly 4 kilometers of Antarctic ice, isolated from the surface for at least 15 million years and almost certainly containing microbial life, established that subglacial liquid water environments are not merely habitable in theory. They are inhabited in practice. The organisms in Lake Vostok have been cut off from sunlight, from atmospheric exchange, from any connection to the surface biosphere, for longer than the Antarctic ice sheet has existed in its current form. They survive on chemical energy alone. If the Martian radar detections represent liquid water, kept liquid by the depressive effect of dissolved salts on the freezing point, or by residual geothermal heat from the planet's interior, or both, the habitability question is not abstract. It is the same question already answered in Antarctica, asked in a different location. The InSight lander, which operated on the Martian surface from November 2018 until December 2022, added a relevant piece of information. Its seismometer detected hundreds of Marsquakes during its operational lifetime, far more than most pre-mission models had predicted for a geologically quiet planet. Mars is not as geologically dead as it appears from the surface. The interior retains heat. Volcanic activity in the Elysium Planitia region, near InSight's landing site, appears to have occurred within the last few million years, geologically recent. The heat that kept the Martian interior active enough to generate those Marsquakes is the same heat that could, in the right subsurface geometry, maintain pockets of liquid water today. Scientists still don't know whether Mars has active subsurface liquid water environments capable of supporting life. The InSight seismic data is suggestive but not conclusive. The Mars's radar detections remain interpreted. No mission currently approved has the capability to investigate the subsurface directly at the relevant depths. What is known is this: the geological conditions that would be required for subsurface habitability, residual geothermal heat, saline water with a depressed freezing point, rock chemistry capable of supporting chemolithotropic metabolism, are all present on Mars in some form. The question is whether they occur together, in the same place, at sufficient scale. There are theories. None of them fully accounts for all the data. And the data itself is incomplete in ways that feel, to the researchers working with it, less like a closed case and more like a door that hasn't been opened yet because the right key hasn't been built. Somewhere in the Martian subsurface, something is either happening or not happening. Chemistry is either crossing a threshold or it isn't. And the instruments capable of telling us which, the drill, the deep radar, the sample return mission that could bring the Wildcat Ridge cores to Earth-based laboratories, are either in development, unfunded, or years from launch. The question waits, as it always has. There is no sunrise here. There has never been a sunrise here. This world left its star, or was pulled from it, or drifted from it in some ancient gravitational negotiation that ended long before anything on Earth had eyes to witness a morning, and has been traveling through the dark between stars ever since. For billions of years, it has moved through interstellar space without destination, without orbit, without the rhythm that a sun imposes on a world. No seasons, no tides, no days. Only the traveling dark, and the cold, and the silence of a world entirely alone. The surface is ice, not the blue-white ice of Earth's polar regions, which carries within it the memory of atmosphere and weather and the slow compression of snowfall over centuries. This ice is older and quieter than that. It formed when the last internal heat of the planet's young life finally conducted upward through the rock and escaped into space, and the water that had pooled in the low places froze, slowly, completely, and stayed frozen. The surface has not changed since. Long fracture ridges run for thousands of kilometers where the ice contracted as it cooled, splitting along lines of weakness like the grain of old wood. The ridges catch starlight and hold it in pale blue-white lines that cross and recross the surface in patterns that have no name. The starlight here is extraordinary. No atmosphere to scatter it, no moon to compete with it, no light pollution of any kind from any source in any direction for light years in every direction. The galaxy arches overhead in its full detail, not the faint smear visible from Earth's surface on a clear night, but the full structure of it, the core blazing amber at the center, the spiral arms tracing their slow curves outward, 10,000 light-years of stellar density rendered in cold, unwavering light against a black so absolute it seems less like a color than like an absence of the concept of color. It is very beautiful here. It is also very cold. The surface temperature is somewhere near 30 Kelvin. Cold enough that the ice no longer behaves quite like ice in any familiar sense. More like stone, brittle and dense and permanent. The faint warmth of the galaxy above does not reach it. The faint warmth of the planet's own interior, still present, still flowing upward through kilometers of rock from the original heat of formation, dimmed now to almost nothing but not entirely gone, rises through the ice in quantities too small to measure without instruments, warming nothing, changing nothing, simply continuing because heat moves toward cold, and has always moved toward cold, and will always move toward cold, as long as the universe maintains the distinction between the two. Deep below the surface, in the dark interior of this world, the rock is still. No earthquakes, no volcanic activity, no convection in a mantle long since cooled below the temperature of motion. Just rock, dense and dark and patient, carrying its residual warmth upward in the slowest possible way, degree by fraction of a degree, through kilometers of silence. The ice fractures catch the starlight and let it go. The galaxy turns above, so slowly that no measurement taken in a human lifetime would detect the motion, but turning nonetheless, everything orbiting everything, the whole vast structure rotating around its own center in a circuit that takes 225 million years to complete. This world has completed perhaps 20 of those circuits since it formed. It will complete many more. Mars kept its silence, as it always has. And the rogue world drifted on in its own quiet, carrying nothing and remembering nothing, and continuing, as all things continue, through the dark between stars that pays it no attention and asks nothing of it, and will receive it eventually, wherever it is going, with the same indifference it has always shown to everything that moves through it. The ice is still. The stars are still. The cold is complete and even and very old. 38 titanium tubes, each one roughly the size of a cigar. Each one sealed, labeled, and cached at one of two depot sites on the floor of Jezero crater. One set left deliberately by Perseverance at a location called Three Forks, in case the rover is unable to deliver them to the retrieval lander itself. 38 samples of Mars, gathered over 3 years of careful, deliberate drilling across the crater floor and the delta fan, including the cores from Wildcat Ridge that carry the organic signals we've spent this night examining. They are sitting on the surface of Mars right now. The retrieval mission, a joint effort between NASA and the European Space Agency, involving a lander, a small rocket to launch the samples into Martian orbit, and an Earth return vehicle to carry them home, has faced budget pressures and schedule revisions since its initial planning phases. The timeline, as of the most recent public statements from both agencies, places sample return no earlier than the mid-2030s, perhaps later. That is not a failure. It is the pace of real science, constrained by real budgets and real engineering challenges. The samples are preserved. The titanium tubes are sealed. Mars's cold, dry, radiation-free subsurface conditions, once the tubes are covered by even a few centimeters of dust, are actually excellent for long-term organic preservation. The molecules in the Wildcat Ridge cores will still be there whenever the retrieval mission arrives. And when they do arrive on Earth, when those cores are finally opened in a terrestrial laboratory, analyzed by instruments that can measure isotope ratios to parts per trillion, image molecular structures at atomic resolution, run every test that the brightest analytical chemists on the planet can devise, the question will get its best answer yet. Not necessarily a final answer. Science rarely delivers those cleanly, but the best answer yet. Until then, the evidence is what it is. A pattern that capable, careful scientists cannot fully explain without biology. A set of molecules in a geological context that, on Earth, has one predominant source. A methane signal that fluctuates in ways that abiotic chemistry struggles to account for completely. A subsurface that may, or may not, still harbor the liquid water and chemical energy that life requires. The data sits in the ambiguous middle, which is, for now, exactly where it belongs. But there is something in that ambiguity worth sitting with for a moment, before we leave the science behind and follow the thought to wherever it leads. Because the question of life on Mars is not, at its core, a geological question. It is not even a chemistry question. It is the oldest question conscious beings have ever asked about the universe they find themselves in. Are we the only ones? And for the first time in the history of that question, after centuries of telescope observations, after decades of missions, after Viking and Pathfinder and Opportunity and Curiosity and Perseverance, after all the careful work of all the careful people, the answer is not a clear no. It has never, before now, been anything other than a clear no. Think about what confirmation would actually mean. Not the headline, not the press conference, not the cultural moment of a president at a podium or a ticker tape across a news channel. Set all of that aside and think about the structural implication, the thing that would quietly change, permanently, in how we understand the universe we live in. If life arose independently on Mars, even once, even briefly, even in the form of a single microbial community in a shallow crater lake 3.7 billion years ago that died out when the water did and left nothing behind but degraded molecules in mudstone, then life is not an accident that happened once on one unremarkable planet, in one unremarkable solar system, in one of 2 trillion galaxies. It is something the universe does. That distinction is not poetic. It is mathematical. One data point is a curiosity. One planet with life could be anything: a fluke, a statistical outlier so improbable that it may never happen again anywhere in the observable universe. One data point cannot define a pattern. It can only suggest one. 2 data points, 2 neighboring planets, both small and rocky and water-bearing, both in the same solar system, both in the same few hundred million years of their formation. 2 data points define a line. They suggest a rate. They imply that given the right conditions, life does not merely have the potential to emerge, it emerges. The universe contains, at current estimates, somewhere between 2 and 3 trillion galaxies. Each galaxy contains, on average, several hundred billion stars. The fraction of those stars with planets is now estimated, based on data from the Kepler Space Telescope and its successors, to be close to 1. Nearly every star has at least 1 planet. The fraction of those planets in the liquid water zone of their star is lower, but still substantial. The numbers involved are so large that even a vanishingly small probability of life per planet produces, when multiplied across the full count, a result that strains the concept of loneliness. And if that probability is not vanishingly small, if 2 data points from a single solar system suggest that life emerges reliably, perhaps inevitably, given water and chemistry and time, then the result of the multiplication is not merely large, it is incomprehensible. There is something strange about standing at that thought. Not thrilling exactly, not the uncomplicated excitement of a discovery. Something more like the feeling of looking down from a very great height and realizing that the ground you assumed was solid is, in fact, the top of something much taller than you knew. Not fear, not vertigo, something quieter than both of those. A recalibration. The sense of a frame expanding around you until the edges of it are no longer visible. We have built our entire civilizational self-image around a specific assumption: that whatever we are singular. That consciousness, complexity, the particular quality of being alive and aware and able to ask questions about the nature of existence is something that happened once and produced us and has not happened anywhere else. That assumption sits beneath almost every philosophical and religious framework our species has built. It is so foundational that most people don't experience it as an assumption at all. It feels like a fact, the way the ground feels solid. The molecules in the Wildcat Ridge mudstone do not disprove that assumption. Not yet. Maybe not ever. The confirmation may never come, may always stay just beyond the reach of what current instruments can settle. But they have made the assumption feel, for the first time, genuinely uncertain. And uncertainty about something this large is not a diminishment. It is the beginning of a much larger understanding, one that our species has been circling for as long as we've been able to point at the sky and wonder what was out there, moving through all that dark, in all those other places, in all that unimaginable time. The cloud is dark from the outside. From any distance, it appears only as an absence, a region of sky where the stars simply stop, where the light from everything behind it is absorbed before it can reach any eye or instrument pointed in this direction. Not darkness in the way a room is dark when the lights are turned off. Darkness in the way a deep place in water is dark. Not empty, but full of something that does not permit passage. Inside, the cold is profound, 10 degrees above absolute zero. The gas here, hydrogen mostly with traces of carbon monoxide and ammonia and water ice crystals so small they are closer to chemistry than to weather, moves in slow currents determined by gravity and by the faint threading of magnetic field lines through the cloud's interior. The motion is imperceptible at any human timescale. It has been moving this way for millions of years. It will continue moving this way for millions more before anything here changes enough to notice. The silence is the silence of compressed waiting, not emptiness, potential. The difference between a held breath and no breath at all. Deep inside the cloud, where the density of gas is highest and the temperature drops another degree or two toward the cold that has no lower edge, something is beginning. Not quickly, not dramatically. Gravity is drawing threads of gas inward along invisible lines of force, pulling them toward a center that does not yet exist except as a tendency, a direction, a slow preference of matter for less distance between itself and other matter. It will take 100,000 years, then another 100,000, then more. The infall is gradual, the compression gentle, the heat produced by the gathering so slight that it would be undetectable from outside the cloud for most of that time. The gas does not know what it is becoming. It only knows inward. It only knows the slow tightening of the distance between one part of itself and another, the gentle pressure of accumulation, the warmth that builds so slowly it barely registers as change until it has been building for a very long time. Somewhere in the dark interior, a knot of gas crosses a threshold. Not violently, not in any way that would be visible from outside, or even from inside without instruments sensitive enough to detect a change in temperature measured in fractions of a degree across a volume the size of a small solar system. But the threshold is real. The density has reached a point where the pressure at the center is sufficient to begin, just begin, the slow fusion of hydrogen into helium, the first tentative glow of a star that does not yet know it is a star. The cloud does not change around it. The dark holds. The cold continues. The slow currents of gas move in their unhurried paths along the magnetic field lines. The outer regions of the cloud are the same as they were 1 million years ago, and will be the same 1 million years from now, dense and dark and patient, doing the one thing gravity has always asked of matter, drawing closer. Somewhere tonight, a scientist is looking at the same data for the 43rd time. Not because the analysis is incomplete, not because the numbers have changed, because the numbers are so close to something, so precisely positioned at the boundary between what can be said and what cannot yet be said, that looking at them again feels less like repetition and more like vigil. The kind of attention you pay to something that matters enough to stay with, even when staying with it yields nothing new. The office is probably quiet, late. The kind of late where the building has emptied and the only sounds are the climate control system and the faint electronic hum of the workstation, and occasionally the distant sound of a door somewhere in the corridor. The city outside is doing whatever cities do at this hour. The researcher does not notice. On the screen, a spectrum, a series of peaks at specific wavelengths, each one corresponding to a molecular bond vibrating at a characteristic frequency when struck by a deep ultraviolet laser. Each peak is a fingerprint. Each fingerprint is a molecule. And the arrangement of those peaks, their positions, their relative heights, the subtle shape of each one, is the thing that cannot quite be explained. Sunanda Sharma has returned to this data more times than she has publicly said. Jennifer Eigenbrode, who published the organic molecule findings from Gale Crater in 2018, after 3 years of careful, methodical elimination of alternative explanations, has given many interviews since. In none of them has she claimed more than the data supports. In none of them has she walked back the significance of what she found. She speaks about it the way you speak about something you are still close to, carefully, precisely, with a steadiness that is not the steadiness of certainty, but the steadiness of someone who has decided to stay with an honest answer rather than reach for a comfortable one. There is something in that carefulness worth noticing. These are not people chasing headlines. They have watched what happens to Mars researchers who overreach. The long shadow of ALH 84001. The careers spent defending claims that the data could not fully support. They know the cost of saying too much. They say, consistently and precisely, exactly what the evidence allows. And what the evidence allows, in their careful language, is consistent with. That they continue to say it, that they return to the data, refine the analysis, run the laboratory comparisons again, submit to peer review again, stand at podiums and choose every word with the particular attention of people who understand that the words themselves carry weight, is its own kind of statement. Not about what they have found, about how seriously they are taking what they have found. The rocks in the titanium tubes are waiting too, in their own way. Sealed, cold, sitting on the floor of a crater on a planet that is, tonight, roughly 140 million miles from where you are lying. The molecules inside them have been waiting 3.7 billion years already. A few more decades is nothing. And the scientists who put them there, who drove a rover across an ancient lake bed and drilled into sediment that no instrument had ever touched, and sealed it into metal and cached it in the Martian dust, are waiting with the particular patience of people who know that the question they are asking is the right one, and that the answer, whatever it turns out to be, will have been worth every careful year spent approaching it. They keep asking. Mars keeps its silence, as it always has. And somewhere in that silence, either something is, or something was, or something waits. The distinction between those three possibilities is, for now, in the data. Patient, precise, and not yet fully read. The rock at Wildcat Ridge is still there. Most of it, anyway. The cores are gone, sealed in their tubes, cached in the Martian dust a few hundred meters away, waiting for a mission that hasn't launched yet. But the outcrop itself remains. The layered mudstone, the carbonate silica matrix, the remaining organic signals that Sherlock's laser mapped, and the team's algorithms parsed into peaks, and the researchers stared at until the patterns were as familiar as a face. We still don't know what put those molecules there. We may know someday. The sample return mission, when it comes, will give the best analytical minds on Earth their turn at the question, and the instruments they will bring to it make everything flown to Mars so far look preliminary. There may be an answer. There may be several answers. There may be a result that settles the question in one direction so cleanly that looking back at this moment, this careful, ambiguous, quietly extraordinary moment, will feel like looking at the last night before something changed. Or the mystery will deepen. That happens too. The truest things tend not to resolve. They settle instead into something you carry, not as a problem waiting for a solution, but as a presence, a weight that is not uncomfortable. The particular feeling of a question large enough to be worth holding without knowing the answer, for as long as it takes, in the company of everyone else who has ever pointed at the sky and wondered whether something was out there, in all that dark, in all those other places, looking back. And Mars kept its silence, as it always has. If this long night with Mars, with the questions it has carried for billions of years, and the careful people who carry them now, helped you find some quiet tonight, we're glad you were here. There are more nights like this one. More questions will follow slowly, together, into the dark. You'll find them where you found this. Until next time, rest well. The cosmos will still be here tomorrow. The Martian night is long. 12 hours of cold and darkness on the floor of Jezero crater. The rover has powered down its non-essential systems, warm inside its electronics bay, waiting for the sun to return. The dust on its solar panels catches no light. The camera eyes are closed. The instruments rest. The crater is very still. The fine sediment on the lake bed, the ancient rust-colored silt that has been lying here undisturbed for longer than the concept of a year has existed, does not move. The wind that lifted it earlier in the day has quieted. The Martian atmosphere, thin and cold and dark, presses down on everything at a pressure no human hand could feel, so slight it barely registers as presence. The sky above is full of stars. From the surface of Mars, the stars do not twinkle. There is almost no atmosphere to scatter their light, no weather to blur them, no moisture to soften their edges. They are sharp and cold and very bright. Among them, in the constellation we call Gemini, 2 points of light sit close together, blue-white, faint. One is Earth, the other is the Moon. From this distance they are inseparable, a single soft glow in a sky of hard, bright points. Everything is still. The 2 small moons have set. The larger one, Phobos, will rise again in a few hours, moving east to west, opposite to the stars, completing its low, fast orbit so quickly that a patient watcher could see it move. But there is no watcher here. Only the rover, resting. Only the rock. Only the long Martian night doing what it has always done, turning slowly on its axis, carrying the darkness from one horizon to the other in its own unhurried time. The samples are nearby, 38 titanium tubes sealed and cached and cold. The molecules inside them are unchanged. They have been unchanged for 3.7 billion years. A few more hours of darkness changes nothing. The crater rim catches the faintest starlight at its highest points. The ancient delta fan, visible in daylight as a low, raised structure at the northern edge of the crater, disappears into darkness. The layered rocks, each layer a chapter, each chapter longer than anything, are invisible now, indistinguishable from the dark. The whole world is dark. The whole world is quiet. The whole world is patient in the way that only very old things can be patient, having outlasted everything that ever pressed against them, having simply continued while everything else changed around them, having arrived at this particular night as they have arrived at every night, without urgency and without complaint. Moving outward now, past the 2 small moons in their low orbits, past the thin halo of the Martian atmosphere, catching the last faint warmth of sunlight on the night side. Out into the space between planets, clean, cold, empty in the way that only space between planets is empty, which is to say, not truly empty, threaded with solar wind and magnetic field lines and the occasional tumbling rock, but quiet, deeply quiet. The sun from here is bright, but smaller than it appears from Earth. Its light takes 4 minutes longer to arrive. The asteroid belt drifts in its slow, scattered orbits, unremarkable from any distance, each rock following its own path with the patience of objects that have no other option and require no other purpose. Farther out, the gas giants in the outer solar system receive sunlight so thin and cold it barely warms them. Jupiter turns, its bands of cloud moving in slow differential rotation, its great storm system, smaller now than it was a century ago, still large enough to swallow the Earth, cycling quietly in its permanent spiral. No sound crosses the vacuum between it and anything. It turns and the light catches its upper clouds and scatters, pale and faint, into the dark in all directions. Saturn's rings catch the sunlight better. From the right angle, at the right distance, they glow, thin, impossibly thin for their width, a flat plane of ice and rock reflecting light that traveled 800 million miles to reach them and will travel much farther before it fades. The rings are silent. Everything here is silent. The silence has texture, the way deep water has texture. A presence rather than an absence, something that presses back gently when you lean into it. Beyond the planets now, the heliopause, the boundary where the solar wind finally weakens enough that interstellar space begins, is crossed without ceremony. No line, no shift, just the gradual change from one kind of emptiness to another. The Voyager probes are somewhere out here, moving at their own slow speeds, carrying their gold records into a dark that will hold them essentially forever. They have been traveling for decades. They are barely gone. The interstellar medium is cold hydrogen and helium in long, slow streams, moving in currents determined by pressures too vast and too gradual to perceive. A thin gas of unimaginable extent, drifting in the spaces between stars, occasionally compressed by the passage of a shockwave from a distant supernova, occasionally seeded with heavier elements cooked in stellar interiors and scattered by stellar deaths, carrying in its composition the entire history of the galaxy's nucleosynthesis. Every element heavier than hydrogen, built in stars, dispersed, recollected, built again. Everything that exists was built in a star. The galaxy turns above, or below, or around, depending on where you stand, because out here the concept of a direction loses its meaning. The Milky Way from outside is a disk, flattened, with a central bulge that glows amber from the density of old stars packed close together, and arms spiraling outward in curves that take hundreds of millions of years to trace. Globular clusters, ancient, dense collections of hundreds of thousands of stars, orbit the galaxy at distances that keep them largely outside the plane of the disk, moving in long, elliptical paths that predate the spiral structure they circle. They are older than most of the stars in the galaxy itself. They were already old when Earth formed. They drift in their orbits. The galaxy turns. The light from 2 trillion other galaxies crosses the void in all directions, some of it ancient enough that the galaxies that produced it have since changed beyond recognition. The light still traveling, still carrying its information about a state of affairs that no longer exists, crossing distances so large that the universe itself has expanded measurably since the light was emitted. The cosmic microwave background is everywhere, not a place, a condition. The entire sky, in every direction, filled with the faint thermal radiation of a universe that was once very hot and very dense, and has been cooling and expanding ever since. It is 2.7 Kelvin now. It was once the temperature of a star's surface, filling the entire volume of everything. That was 380,000 years after the beginning, when the universe first cooled enough for light to travel freely instead of scattering off a plasma of charged particles. The light that escaped in that first moment of transparency is the microwave background. It has been traveling ever since. It passes through everything. It passes through you, the oldest light there is, everywhere at once, everything continuing. The rover on the Martian crater floor, the titanium tubes in the Martian dust, the molecules inside them, unchanged for 3.7 billion years, waiting with the patience of things that do not know they are waiting. The scientists at their workstations, the data on the screens, the peaks in the spectra that do not move and do not change and do not offer more than they have already offered, which is exactly what they are, neither more nor less, sitting in the record of a careful instrument on a distant world, as quiet and as present and as still as everything else, in all of this that has ever simply continued. The stars are very bright tonight. The dark between them is very soft. Everything is very still, and Mars kept its silence, as it always has.